A covalent bond is a chemical bond in which two or more electrons are shared by two atoms. Why should two atoms share electrons? Let's take a look at these two fluorine atoms. They can come together and bond together and form fluorine, F2. Each of the two fluorine atoms has 7 valence electrons. When they bond together, they share the unpaired electrons, so that now they both have an octet. The Lewis structure then of F2 would look like this with the dots, or we can replace the shared electrons with a dash. We have lone pairs of electrons on the valence level that refer to electrons not involved in bonding. Each fluorine atom has 3 lone pairs. The molecule itself has a total of 6. We have one bonding pair that gives us that single covalent bond. Sometimes you're going to be asked how many lone pairs of electrons there are, or how many bonding pairs of electrons there are in a molecule. So here we have some more diatomic elements. You can put a bond here between the two fluorine atoms like we had a moment ago. The oxygen atoms, because they have 2 unpaired electrons, can share both of those pairs. And the nitrogen with 3 unpaired electrons can share all 3 pairs. And so we wind up with a single, a double, and a triple bond in these 3 diatomic molecules. How many lone pairs? Well, we can count them right here. 6, 4, and 2. Now in this slide we're taking a look at the single, double, and triple bond, and a couple things to note. First of all, that the single bond is the longest of the 3 and the weakest. Weakest meaning is the easiest to break. Whereas the triple bond would be the shortest and the strongest. You can see this verified in these table of bond lengths and bond energies. So if you compare the first 3 bonds, you notice how the energy increases and the length decreases. Also notice that the amount of energy doesn't double from a single to a double. Doubling would make it almost 700, and this is a little bit less than that. So we might have a double bond, but the 2 bonds aren't really equal. It's more like 1.5 or 1 3/4 of a bond. Because the single bond is the longest and the weakest, that means that the F2 molecule is the most reactive of the 3. In fact, the N2 molecule is so unreactive that most of our atmosphere is made up of this, and we breathe it in, we breathe it out, we can't do anything with it. But it also means that when N2 is formed in a chemical reaction, there's an awful lot of energy released from that triple bond forming. Now let's take a look at water. We saw this before. We have an oxygen atom with 2 unpaired electrons. We have a hydrogen atom we can bring in to make a bond here, another one make a bond here, and then we wind up with our structure for the water molecule. 2 lone pairs of electrons and 2 bonding pairs. Now we can take a look at ammonia. Take a look at the nitrogen atom first. Notice it has 3 unpaired electrons. So we're going to bring in 3 hydrogen atoms and bond them together like that. And then we can replace the bonding electrons with a dash. And here's our Lewis structure for ammonia. 3 bonding pairs, 1 lone pair. There are rules for drawing Lewis structures when you already have a formula. I'm going to go through that, and then we're going to draw out maybe 5 different molecules. First thing is to count all the valence electrons that are present in the molecule. Then we're going to draw the molecule. And if we have a molecule made up of at least 3 atoms, but only 2 elements, we're going to put the atom that's all by itself. Like for instance, if we had CO2, we'd put the carbon in the middle and then put the oxygens on either end of it. So we have to know how to set it up first. We're going to use a pair of electrons to bond the atoms together. And then we're going to complete the octets of all the atoms in the molecule, except for hydrogen because it doesn't have an octet. We will do the central atom last whenever we draw out molecules of at least 3 atoms. Now I'm going to go through drawing out some of these. If you want to try them on your own first, that's fine, but I will do them one at a time. Let's take a look now at the carbon tetrachloride. What we have is we have my arrow here. We have 4 valence electrons from the carbon, and we have 4 chlorines. Each chlorine has 7 valence electrons, for a total of 32 electrons. So I'm going to get my pen here. First thing I'm going to do is bond the atoms together by using a pair of electrons. And then I would complete the octets until I run out of electrons. don't have to be real neat with this as long as we get them all in there. So you notice now that each chlorine atom has an octet and the carbon has an octet. So now I'm just going to replace those bonding electrons with a dash. 1, 2, 3, and 4. And then I also put my lone electron pairs in. And there we have it. So this is the Lewis structure for carbon tetrachloride, 4 bonding pairs and 12 lone pairs. Next we have CO2. Okay, so we have 4 for the carbon and 2 times 6 for the oxygens. That's 16 electrons. So we start by bonding the carbon to the oxygens. We're going to go around the oxygens until I run out of electrons. And now that's 16 electrons. If the carbon doesn't have an octet, it only has 4. So I'm going to have to form multiple bonds for the carbon to get an octet. I'm going to bring a pair of electrons here and here up. So it looks like this. So these are my bonding electrons. Now the carbon atom can form multiple bonds. One reason why carbon is so reactive. Okay, I'm going to replace those bonding electrons with a dash. And there we go. So that's the Lewis structure for carbon dioxide. So what did you notice? The central atom didn't have an octet. We had to form multiple bonds so that the carbon atom could have an octet. So normally carbon atoms form 4 bonds, but it can be any combination of 4. 4 singles, 2 doubles, a triple and a single. Any combination will give us 4, even a double and 2 singles. All right, now we're going to do sulfur dioxide over here. There will be 18 valence electrons. And we start by bonding sulfur to the oxygens. We're going to go around. And that's all 18. So the oxygens are all set, but you notice the sulfur in the middle, 2, 4, 6, only 6. So I'm going to have to form a double bond with one of these oxygens. I think I'll pick the one on the left. I could pick the one on the right too, that won't matter. Okay, so this oxygen has 8, sulfur has 4, 6, 8. This oxygen has 2, 4, 6, 8. Good. Now I'm going to replace the bonding electrons with the dashes. Good. It's important not to put in too many electrons, so make sure you just use up the total that you determined in the beginning. So there's the Lewis structure for sulfur dioxide. We have a double and a single bond. We have 1, 2, 3, 4, 5, 6, 7 lone pairs of electrons. Next we have carbon monoxide. That has a total of 10 valence electrons. So let me start here, bond them together. And quickly I use up my 10. But the carbon again only has 4 electrons. So I'm going to have to bring up 2 pairs and add them to the pair that's already there. So this is going to give me a triple bond. So you notice now I have my 10 electrons. These 6 count for both atoms. So the 6 and 2 for 8, 6 and 2 for 8. So that means I have a triple bond. Within carbon monoxide. Now the next one we have here is a polyatomic ion. You can see the negative charge on it. And this is only going to affect the total number of valence electrons. So we have 4 from the carbon, 3 oxygens are 3 times 6, and I'm adding 2 more because of the negative charge. If this had been a positive charge, I would have subtracted the number of the positive charge from the total. So I have 24 electrons. So we start off by bonding the atoms together. Go around and do the oxygens. And now I have all 24 electrons. Notice though the carbon only has 6. So I'm going to have to form a double bond with one of these oxygens. I think I'll pick the one on the left here. So there'll be 2 electrons like that. So there, now my octet for the carbon is all set. I'm just going to fill in then for the other oxygens. Okay, so this becomes then a double bond here, and then 2 single bonds. And I put in my electrons. Okay, so we're all done. Now, one thing they usually do with the polyatomic ions is they will enclose it in brackets, and then you see the charge on the outside. There we go. So that's our carbonate ion. Now, sometimes molecules can form more than one structure by simply moving a double bond around. And my example here is ozone, which is O3. If you were to draw out ozone, you would have come up with this for its structure. But you notice I could put the double bond between either of these oxygens here. So some people think that these kind of structures rotate from one to the other, and that's kind of like what this double bond means. Studies show that the bonds, though, are really the same, so we really don't have a double and a single bond here present, but it's just that that's all the only way we can draw them if we follow the rules for Lewis structures. So some people will say, you know, the bond is really more like this. It's more of something between a double and a single. So many of the substances that I drew out already, if they had a combination of a double and a single bonds in there, they could form resonance structures, just like we see for the ozone. So you might see some questions in the text that'll ask you to draw all the resonance structures of a particular compound. So let's see about the carbonate ion, which we drew a moment ago. What would its resonance structures look like? Well, here they are right here. You notice that we have the double and the 2 singles, and all I'm doing is kind of moving that double bond around. So the carbonate ion has 3 resonance structures. Okay. Now sometimes more than one structure can be drawn for the same particle. How do you know which one could be correct? CO2 could be this. This is the way we drew it before, but it also could have been this, because this would also follow the rules. So how do we know? I'm going to get my arrow back again here. Let's see. No, I don't want that. Good. Okay. Concept of formal charge can help. So a formal charge isn't a real charge. It's a charge that's given to each atom in a molecule. In order to calculate a formal charge, we just have to look up the valence electrons for each atom, and then we're going to subtract from them the electrons that we've given them in the particular structure. When you see one done out, it'll make sense. So here we start off with our 2 possible structures for carbon dioxide. So here we are here now. So my valence electrons would be 6, 4, and 6. 6 because group 6 for oxygen, 4 for carbon. Okay, so that's no different. But the assigned electrons are a little bit different. Now for the assigned electrons, you can see the ones I have, 1, 2, 3, 4 for this particular oxygen. And now I have a double bond. For each bond, I'm going to take an electron and give it to that particular atom. So this oxygen atom has 2, 4, 5, and 6. The carbon has 1, 2, 3, 4. And this guy would have 2, 4, 5, and 6. Okay, good. Now let's see what it does on this side, though. This particular oxygen atom has 2, 4, 6, and then 1 for 7. The carbon has 1, 2, 3, 4, and this oxygen has 1, 2, 3, 4, 5. So you see what happens when we subtract them. We get all zeros over here, but here we get some other numbers of -1 and a +1. The total will add up to whatever the charge is on the particle, which is neutral in this case. So the Lewis structure with no formal charges is the better one. That's what we're looking for. That means that's the better structure. So if sometimes you have the possibility of using different types of bonds like this, This is the idea of formal charges is used to determine which is the best structure. Okay. Now these are the rules for formal charges. Sum of the formal charges for molecules will be 0. The sum of the formal charges for ions is whatever the charge of the ion is. And hydrogen will always be given a charge of 0. So how about if you try to find the formal charges for NO2 minus? Now you want to pause, maybe try this on a piece of paper, and then you can go back and see the answer. Okay, now here's the answer. Here we go. So for our valence electrons, 2, 4, 5, 6. The nitrogen, 1, 2, 3, 4, 5. The oxygen, 1, 2, 3, 4, 5, 6, 7. And you notice we get minus 1. And minus 1 happens to match up with the charge up here. So, there we go. Okay. Now there are exceptions to the octet rule. There's an incomplete octet, which we can see. I'm going to get rid of my my arrow here. Go back to the arrow options. Okay. So here we go. BeH2 and BeH2, beryllium hydride, doesn't have an octet at all. Beryllium, beryllium, remember, if you look at the periodic table, just has 2 valence electrons. So this is its structure. Here's our 2 covalent bonds. And this is what the molecule would look like if you use models. Bf3, boron, has only 3 valence electrons. And you see how it would be arranged like this. So boron cannot form any double bonds. And we get 20-foot total electrons. Odd electron molecules, here's one, NO, which is nitric oxide. 11 electrons altogether. And that's what it will look like. You can't just get an octet there. So there are such things in nature. And then we have an expanded octet. This is sulfur hexafluoride. A lot of electrons. And you notice that the sulfur is forming 6 bonds here. And we saw that earlier. Sulfur can do this because it can bring the valence electrons in the d orbitals. Okay, and that's the end of the show.